Hi everyone, I'm Adrian from the Australian Computer Museum, or the ACMS, based here in Sydney, New South Wales, Australia. At the ACMS, we have one of the largest digital equipment corporation collections anywhere in the world. We were founded in 1994 by many people, including Max Burnett, one of the first employees of Digital Australia. DEC was founded in 1957 in Maynard, Massachusetts, and grew to be one of the largest computing companies in the world. In our collection, we have a significant amount of documents, computers, and training material. And today, we're going to present some of that training material to you in the form of old VHS tapes. So, please sit back, relax, and enjoy. Thank you.
All computers and workstations in the VAX family incorporate the same 32-bit architecture. This common architecture ensures a high degree of compatibility among VAX computers. Programs written to run on one VAX machine will run on any other processor in the VAX family. In this unit, we'll look at typical hardware implementations of the VAX architecture. Our discussion is divided into 3 lessons. The first 2 lessons develop this basic model of a VAX system, a system that's configured with a single CPU. Lesson 1 concentrates on the Central Processing Unit, or CPU. It introduces you to the hardware features shared by most VAX processors. Lesson 2 covers the other parts of our model, the console subsystem, memory, and the I/O subsystem. Lesson 3 describes VAX systems that are configured with 2 or more CPUs. You'll learn about multiprocessor systems, such as this VAX cluster.
Physical parts common to a VAX system include the Central Processing Unit, or CPU, a console subsystem, main memory, and an I/O subsystem. A bus interconnects the CPU with memory and the input-output subsystem. This bus carries the addresses, data, and control information that are exchanged between the hardware subsystems. The CPU is the hardware element that controls the VAX system and executes programs. Key components within the CPU include this set of general registers and a processor status long word, or PSL register. There's also a cache memory and the arithmetic logic unit, or ALU. All VAX processors contain 16 general registers, numbered R0 through R15. Each register holds 32 bits of information. 4 of these registers are dedicated to specific uses. The others are available for general use by the assembly language programmer. For example, 1 or more of these registers can be used for storing data that the ALU is operating on. This allows data to be accessed very quickly because the registers are part of the CPU. The general registers may also be used to access data located outside the CPU. Here, Register 2 contains an address that points to data stored in memory. During program execution, the CPU uses this address to locate the data. In the next unit, we'll have more to say about how these general registers are used. Registers 12 through 15 are dedicated registers. They have special uses that distinguish them from the other general registers. Register 15 is called the program counter, or PC. It contains the address of the next instruction to be executed. Each time the CPU fetches another instruction from memory, the address in the PC is updated automatically, so it's pointing to the next instruction. So Register 15 always functions as the CPU's program counter. Register 14 functions as the stack pointer, or SP. This register points to the top of a special data structure called a stack. The stack is used in a number of ways, including interrupt processing and parameter passing. For example, before the CPU processes an interrupt, it saves the contents of selected registers on this stack, so the registers can be restored to their current state after the interrupt is serviced. The stack works on a last-in, first-out principle. That is, the last item of data saved on the stack is always the first to be removed. Each time another item is added to the stack or removed from it, the address in the stack pointer is updated automatically. So the stack pointer is always pointing to the top item currently on the stack. Thus, the CPU uses Register 14 as its stack pointer. Registers 12 and 13 also have special functions. They're used when one program calls or invokes another program. Specifically, Register 12 serves as the argument pointer, or AP. Register 12 points to a list of arguments to be passed from the calling program to the program that's being called. The calling program creates the argument list before it transfers control to the other program. This list contains numerical values, addresses, and other items of data to be used or operated upon by the called program. The calling program then places the starting address of the argument list in Register 12, the argument pointer. When the called program begins executing, it uses the argument pointer to access items of data supplied in the argument list. Thus, the CPU uses Register 12 to pass argument lists from one program to another. Register 13 functions as the frame pointer, or FP. It contains an address which points to a data structure referred to as a call frame. A call frame is created and saved on the stack before the calling program relinquishes control to another program. This call frame contains register values and other information that the calling program needs to regain control at a later time. Once the CPU finishes executing the called program, it uses the frame pointer register to locate the call frame that was saved on the stack. The information preserved in the call frame is then copied into the processor registers, thus restoring the registers to the state they were in at the time the call was made. This completes our discussion of the general registers. In addition to the general registers, all VAX CPUs have a processor status long word, or PSL register. This register contains information about the current state of the CPU and the program it's executing. The 32-bit PSL register is functionally split in half. The upper half, consisting of bits 16 through 31, describes the processor state. For example, bits 24 and 25 indicate the processor's current access mode. As you'll learn in Unit 4, the CPU can be operating in any one of 4 access modes: kernel, executive, supervisor, or user. The access mode determines which instructions the CPU is allowed to execute and what parts of memory it's permitted to access. Note that the information in the upper half of the PSL is treated as privileged information. This information can be modified only by VMS. User programs cannot access this part of the PSL. However, user programs can access the lower half of the PSL, consisting of bits 0 through 15. This part of the PSL holds program status information, which changes as a program executes. Often, this part of PSL is referred to as the processor status word, which is abbreviated PSW. The first 4 bits in the PSW are condition code bits. These bits, which are labeled N, Z, V, C, describe the outcome of the most recent instruction executed by the CPU. The letters N, Z, V, C stand for negative, 0, overflow, and carry. Thus, the N condition code bit indicates a negative result. Anytime an instruction produces a result with a negative value, the N bit is set to a 1. Likewise, the Z bit is set to 1 if an instruction produces a result with a value of 0. The remaining condition code bits function in a similar manner. The V bit is set whenever an instruction produces a result which overflows. In other words, the magnitude of the result was too large to be represented. And the C bit is set if an instruction causes a carry or a borrow, involving the most significant bit of the result. Thus, the C bit, together with the other condition code bits, indicate the outcome of each instruction executed by the CPU. Bits 4 through 7 of the PSW are called trap-enable bits. If any of these bits are set to 1, they transfer control to a software routine when certain error conditions occur during a program's execution. For example, suppose a decimal overflow condition occurs while the CPU is executing a program. If trap-enable bit 7 is set to 1, the processor responds by executing a software routine that services the decimal overflow condition. On the other hand, if trap-enable bit 7 is a 0, the decimal overflow condition is simply ignored, and the processor continues normal execution of the program. The other trap-enable bits function in a similar manner. As we noted earlier, the general registers provide temporary storage for data the CPU is working on. Additional storage is built into most VAX CPUs in the form of a small high-speed memory called cache memory. Cache memory can be thought of as a small stockroom located within the CPU. It allows the processor to access information very quickly. However, the cache has a limited storage capacity compared to that of main memory. Main memory, in turn, can be pictured as a large warehouse which holds considerably more information, but requires more time to locate and supply information requested by the CPU. Typically, main memory is 2 or 3 times slower than cache memory. As a program executes, cache memory is continually updated with new instructions and data read from main memory. This means that the cache always contains a copy of the information most recently used by the CPU. If the same instruction or data is referenced again, the information can usually be found in the processor's high-speed cache. This allows the CPU to access information much more quickly by reading directly from its cache instead of going to main memory. The CPU accesses main memory only when the data is not available in the cache. Thus, the advantage of storing data in cache memory is that programs will execute faster, since there are fewer references to slower main memory. The last major area of the CPU we'll discuss is the arithmetic logic unit, or ALU. The ALU operates on data obtained from the general registers and main memory. For example, the ALU performs the standard arithmetic operations: add, subtract, multiply, and divide. It also carries out shift operations, shifting bits 1 or more places to the right or left. And the ALU performs logical operations like and or. The next unit describes the set of instructions that can be executed by the processor's ALU. This completes our discussion of the major hardware elements that form the VAX CPU. To briefly recap, the CPU contains a set of 16 general registers. Data that the processor is operating on is either stored in these registers or is addressed through them. 4 of these registers, R12 through R15, have special uses, serving as the argument pointer, frame pointer, stack pointer, and the program counter. There's also a processor status long word register, or PSL, which is functionally divided in half. The top half contains privileged information describing the processor state. This part of the PSL can be modified only by VMS. The lower half of the PSL contains program status information, which is user modifiable. Cache memory is also part of the CPU. As a program executes, instructions and data are read from main memory and are copied into this cache. Thus, cache memory always contains a copy of the information most recently used by the CPU. If the same data is needed again, it's read from the CPU's cache, thus avoiding additional references to slower main memory. The use of cache memory can improve the overall speed of the computer by 2 or 3 times. This concludes Lesson 1. Before continuing on to Lesson 2, please turn to your course reference guide and review the information for Lesson 1. In Lesson 1, we introduced this model of a typical VAX system and described some of the hardware elements within the CPU. We'll now look at the other subsystems that make up our model. Let's begin here with main memory. Main memory stores and retrieves information processed by the CPU. It consists of 2 parts, a memory controller and 1 or more memory arrays. The memory controller handles all incoming requests to read information from memory or to write information into memory. In addition, the controller monitors the operational status of the memory subsystem and reports status back to the CPU. The memory arrays store instructions and data that the CPU references during execution of a program. In VAX systems, this storage space is divided into smaller units called page frames. Each page frame holds 512 bytes of data. Data within a page frame is accessed by specifying its physical address. The smallest unit of data that can be addressed is the 8-bit byte. Since the byte is part of a larger page frame, its physical address actually consists of 2 parts, a page frame number, or PFN, and a byte offset. The page frame number points to the specific page frame in which that byte resides. You'll recall that this page frame represents 512 contiguous bytes of storage. The byte offset then identifies the location of the byte relative to the beginning of that page frame. For example, a byte offset of 511 designates the last byte in the selected page frame. So the byte offset, in combination with the page frame number, allow the CPU to access any byte stored in memory. This completes our discussion of how memory is organized and addressed in VAX systems. We'll now turn our attention to the console subsystem, which is used for controlling, monitoring, and testing the system. This is a typical console subsystem. It connects with the main VAX CPU by way of a separate bus. The hardware elements that form the console subsystem include a console terminal, a load device, and a console processor. The console terminal serves as the operator's interface to the VAX system. In addition, this terminal can function as a normal user terminal. Through the console terminal, a system manager or service engineer can control and monitor the rest of the VAX system. For example, you can boot the operating system, start or halt the CPU, run diagnostic programs, and examine the contents of selected registers and memory locations. These tasks are performed by entering English-like commands at the console terminal keyboard. Each time a command is entered, it's interpreted and acted upon by the console processor. Most VAX systems have a separate console processor that interacts with the main CPU. A few systems use the main CPU to execute console commands. In addition to the processor and terminal, the console subsystem has some type of load device, either a disk drive or tape unit. This load device stores diagnostic programs, software updates, and bootstrap programs that are used to load the operating system. In addition, it can serve as a storage facility for system data and maintenance information. A remote diagnostic port is also available on most console subsystems. Through this port, diagnostic testing can be performed from another terminal located at a remote facility. Console commands may be entered at the remote terminal to select and run diagnostic programs. As each command is entered, it's transmitted to the console subsystem over standard telephone lines. Test results are then returned to the terminal at the remote facility for interpretation. Thus, system testing can be performed from either a remote facility or from the local console terminal. The final element in our general model of a VAX system is the input-output subsystem. Typically, it consists of an I/O bus adapter, an I/O bus, several device controllers, and a variety of peripheral devices such as printers, disks, and terminals. The I/O bus adapter connects the input-output subsystem to the rest of the VAX system. The adapter serves as the translator or interface between two different buses: the system bus, which interconnects the CPU and memory, and the I/O bus, which is used by all peripheral devices and their controllers. Each bus has its own addressing and data transfer protocol that must be accommodated by the I/O bus adapter. In effect, this adapter allows units connected to the system bus to communicate with device controllers connected to the I/O bus. For example, the CPU communicates with the disk controller by way of the I/O bus adapter and the I/O bus. The disk controller, in turn, manages the flow of data into or out of the disk drive to which it is connected. Data is transferred directly between memory and the disk drive without any help from the CPU. The disk controller also monitors the operational status of the peripheral device and sends status reports to the CPU. If an error occurs during a data transfer, it's reported back to the CPU. A wide variety of peripheral devices may be used with VAX systems, including mass storage devices, such as magnetic disks, optical disks, and magnetic tape units, input-output devices, including terminals, printers, and plotters, and network communications devices, such as Ethernet adapters, terminal servers, and modems. Additional information on these peripheral devices is provided in the VAX Hardware Handbook. This completes our discussion of the hardware elements that form a typical VAX system. These elements include the CPU, a console subsystem, memory, and an I/O subsystem. The CPU executes instructions and controls the rest of the VAX system. Within the CPU are 16 general registers. There's also a processor status long word register, cache memory, and the arithmetic logic unit. Main memory stores instructions and data needed by the CPU. It's functionally divided into two parts: a memory controller, which services all read-write requests, and one or more memory arrays. The memory arrays are organized into smaller storage units called page frames. One page frame holds 512 bytes of data. The console subsystem allows a system manager and maintenance personnel to control, monitor, and test the VAX CPU and other parts of the system. Typically, it consists of a console terminal, a processor that carries out commands entered at the console terminal, and some type of load device. Finally, the input-output subsystem allows peripheral devices to communicate with the rest of the VAX system. An I/O bus adapter, the I/O bus, and various peripheral devices and their associated controllers make up the input-output subsystem. This brings us to the end of Lesson 2. Your course reference guide summarizes the information presented in this lesson. Before starting Lesson 3, you may want to review this material. Also, remember to complete the exercises at the end of the lesson. VAX computers come in a wide variety of models and configurations. Some models use a single central processing unit. Others consist of two or more CPUs that are coupled or linked together so they appear to function as one very large system. In the previous lesson, we developed this model of a VAX system configured with a single processor or CPU. We'll now describe and compare VAX systems that are configured with more than one CPU. These systems fall into three general categories: tightly coupled systems, networks, and VAX cluster systems. A tightly coupled system consists of two or more CPUs that share a common memory. The processors communicate with memory over a high-speed bus or interconnect. The CPUs also share a single copy of the VMS operating system that resides in their memory. And the processors maintain a common file system. In other words, the CPUs can access and use the same files of data. A system of tightly coupled CPUs is similar to this multi-engine aircraft. The engines work together. They share the same fuel supply and are operated by one set of controls. Like the engines in the aircraft, the CPUs in a tightly coupled system work together to share the processing load. The CPUs may be working on different parts of the same job, or they may be working on separate jobs. The processors use the same memory, and they are controlled by one copy of the VMS operating system. When one CPU needs to communicate with another, it does so through the common memory. Thus, memory can be used as a medium for exchanging messages. If processor A wishes to communicate with processor B, it writes its message to memory, and processor B then reads the message. Because memory can be accessed quickly by the CPUs, this method of communication is very fast. A tightly coupled system is well suited for both multi-streaming applications and parallel processing. In either case, the use of multiple CPUs provides increased computer power. With multi-streaming, the CPUs can be working on completely different and independent jobs at the same time. System performance is enhanced because multiple jobs can be running on the processors simultaneously. With parallel processing, the CPUs can be working on different parts of the same application. The application is first broken down into separate independent tasks. Then the tasks are run in parallel on two or more processors. An important advantage of parallel processing is that large compute-intensive jobs can be completed faster. This ends our discussion of VAX systems that use tightly coupled processors. We'll now describe networks, our second category of multiple CPU systems. VAX computers are often linked together to form networks. The computers in a network are very loosely coupled systems. In other words, the CPUs have separate memories, maintain their own file systems, and execute separate operating systems. Thus, a network can be viewed as a distributed system of VAX computers, each controlled by its own operating system. The VAX computers communicate by sending and receiving message packets over the network links. This method of communicating is slower and involves more overhead when compared with communications in a tightly coupled system. DECnet is the communications software that allows VAX computers to talk to each other. DECnet ties everything together so that messages can be sent from one network node to another. To facilitate communications, each node has a unique name, which is used much like a mailing address. Working from a terminal, a network user can easily access applications and resources that exist on other network nodes. To communicate with a remote node, the user simply types in the name of the desired node. DECnet does all the work of making the connection. DECnet supports two basic kinds of network environments: wide area networks and local area networks. In a wide area network, VAX computers and terminals may be physically dispersed over a large geographic area. In general, wide area networks are used for long-distance communications covering hundreds or even thousands of miles. Messages and data are transmitted over telephone lines, microwave stations, satellite links, and other kinds of communications media, which link the various nodes of the wide area network. Often the data is transmitted over several different types of channels before reaching its destination. A local area network, on the other hand, links computers and workstations within a smaller area, such as an office, a building, or complex of buildings. Often, local area networks are used for workgroup computing, a team of people who are working together, sharing information and network resources. In a local area network, the computers and workstations communicate over a serial communications link, such as an Ethernet cable, which interconnects all of the nodes. Individual computers and workstations plug into the Ethernet cable through transceivers, which may be placed anywhere along the cable. Two or more segments of Ethernet cable can be connected through a device called a repeater. The repeater amplifies signals sent over the Ethernet and enables the segments to function as if they were one long cable. To summarize, VAX computers and workstations may be interconnected by physical links to form wide area networks and local area networks. The links provide a communications medium for exchanging data and sharing network resources. The computers in these networks are loosely coupled systems. That is, they have separate memories, file systems, and their own operating systems. VAX cluster systems represent our third category of multiple CPU configurations. Digital offers two types of VAX cluster systems: a CI-based VAX cluster and a local area VAX cluster. These two systems can be joined into a single VAX cluster configuration. A CI-based VAX cluster can be configured many different ways. This particular system consists of 3 VAX computers and 2 mass storage servers. Each of these subsystems forms one node of this 5-node cluster. The VAX computers and servers communicate over the computer interconnect, a high-speed bus which attaches to all cluster nodes. One CI bus is required for each node. Within the CI bus are 4 cables, 2 for transmitting data and 2 for receiving. Normally, both sets of data paths may be used by the VAX computers and mass storage servers. If one path fails, the cluster subsystems can still communicate over the alternate path. The use of redundant data paths enhances system reliability. Each VAX computer and mass storage server connects to the CI bus through an adapter. This adapter is an intelligent hardware interface which handles much of the work of communicating with the other nodes in the VAX cluster. The star coupler serves as the central hub of the VAX cluster. It provides a common connection point for all cluster nodes, so any node can communicate directly with any other node. The CI-based VAX cluster requires an adapter for each VAX computer. The system must also be configured with a star coupler and one set of computer interconnect cables for each node. Optional hardware includes these mass storage servers, which are referred to as hierarchical storage controllers, or more simply, HSCs. The HSCs connect to the VAX cluster by way of their own adapter. Each HSC controls and monitors operations in several disk storage units or tape drives. The disks can be dual-ported to a pair of HSCs, as they are here. File sharing is one of the attributes of a VAX cluster. Files that reside on the disks can be accessed through either HSC and shared by all computers in the cluster. Often a VAX cluster is configured with one or more terminal servers. Several user terminals can be attached to a single server. The terminals connect to the server either directly or through dial-up telephone lines. The terminal server, in turn, connects to the VAX computers via an Ethernet cable. With this arrangement, it's possible to connect any user terminal to any computer in the cluster. If a node fails, the terminal server automatically attempts to switch users to another computer so processing can continue. This cluster of VAX computers resembles a loosely coupled network in some ways and a tightly coupled system in others. On one hand, it resembles a network because each computer has a separate memory and its own copy of the VMS operating system. On the other hand, the VAX cluster has a common file system, a characteristic it has in common with tightly coupled systems. File sharing is possible in a VAX cluster because the VMS operating systems coordinate their activity so the VAX computers appear to function as a single system. This completes our discussion of CI-based VAX clusters. We'll now look at the hardware components that make up a local area VAX cluster. An Ethernet cable provides the common interconnect in local area VAX clusters. Attached to the Ethernet are VAX computers and workstations, which can be distributed throughout a department or building. One computer is set up as the boot node. The other VAX computers and workstations function as satellites. It's also possible to configure the local area VAX cluster with two boot nodes. The boot node generally manages all shared resources in the local area VAX cluster. The system disk, which is accessed through this boot node, provides storage for the VMS operating system, DECnet software, and layered software products. When a satellite member is powered on, a copy of the VMS operating system and other necessary software is loaded over the Ethernet from the system disk. Thus, each satellite is remotely booted from a common system disk. The satellite members may be any combination of microVAXs and VAX stations. Satellites can be configured with their own local disks, or a satellite may be configured as a diskless system. This completes our discussion of tightly coupled systems, networks, and VAX clusters. Let's review and compare these systems. In a tightly coupled system, memory is shared by all of the CPUs. The processors also share one copy of the VMS operating system and maintain a common file system. A network of VAX computers falls at the other end of the spectrum. Each computer has a separate memory, executes its own operating system, and maintains a separate file system. VAX cluster systems fall somewhere in between. The computers have separate memories and their own copy of the VMS operating system, but they share a common file system. This brings us to the end of the videotape for Unit 3. Before starting the next unit, please review the material in your course reference guide. Also, remember to complete the exercises.